Another common type of work problem that you'll see are these propulsion problems. So these are problems where you're taking some object and you're propelling it from the surface of the earth to a certain height, and you want to know how much work is it going to take to do that. So this example says neglecting air resistance and the weight of the propellant, determine the work done in propelling a 10-ton satellite to a height of 11,000 miles above Earth and 22,000 miles above Earth. Now, whenever you're talking about Earth and you're using miles, you can use 4,000 miles as an approximate radius of the Earth, just to keep everything a little bit simple. And keep in mind that the weight of a body varies inversely as the square of its distance from the center of the Earth. So whenever we do these propulsion problems, the force exerted by gravity is F of x equals c over x squared, where c is the constant of proportionality. And that's what we're using to calculate these problems, because basically the object is working against gravity. So when we look at this, because we're looking at the distance from the center of the Earth, if this is the center of the Earth right here, and we've got Earth, or at least a shot of Earth here, a slice of it, we've got this distance from the center to a point on the Earth. The radius here is going to be 4,000 miles. And then for our problem for part A, we want to propel this thing another 11,000 miles. Okay? So just keep that in mind, because that's going to change the bounds on our integral. So we're going to let x equal the distance from the center of the Earth. Okay? And we know, and that's to the object, however far it's going to travel. And we know that f of x is equal to c over x squared. And we're trying to calculate how much it's going to take to get all the way up to 11,000. So we know that on the surface of the Earth, this thing weighs 10 tons, or its mass is 10 tons. I guess it is its weight. That's okay. So what that tells us is that F equals 10 tons when X equals 4,000 miles, because 4,000 miles from the center of the Earth, the force is 10 tons. So we're going to use that to find C. So I'm going to have 10 equals C over 4,000 squared. So that tells me that C equals 10 times 4,000 squared. Now I could multiply that out, but that's going to be a huge number, and it's actually more convenient to write it this way. So we're just going to say that f of x equals 10 times 4,000 squared divided by x squared, and work with that for the rest of the problem. So now for part A, I want to propel this thing 11,000 miles. So I'm going to say that work is equal to the integral of our function 10 times 4,000 squared divided by x squared dx. And we're going to go from 4,000 miles to 15,000 miles, because that's the whole distance here. So that's my part A. 4,000 miles to 15,000 miles. Okay? So I'm going to integrate this. All of this 10 times 4,000 squared is just a constant, and we're really just integrating x to the negative 2 power. So I'm going to carry my constants, 10 times 4,000 squared, and we'll have x to the negative 1 power over negative 1, and that's going to go from 4,000 to 15,000. So I'll have 10 times 4,000 squared times negative 1 over x from 4,000 to 15,000. And that'll be 10 times 4,000 squared. We will have negative 1 over 15,000 minus a negative 1 over 4,000. And if you find the common denominator and subtract that, you get 10 times 4,000 squared times 11 over 60,000. And then when you do the arithmetic here, you end up with 88,000 divided by 3, and that will be in mile tons. So this is the amount of work that it would take to propel this object 11,000 feet from the center of the Earth. Now for part B, of course, you're wanting to go, you've got your 4,000 miles to get here, and you're wanting to go an additional 22,000 miles. So really we're going from 4,000 to 26,000. So work would be the integral from 4,000 to 26,000 of that same function. So the only thing that changes here is the bounds that you plug in. I'll leave this one for you to calculate, but we've at least got the setup for it. This one says a lunar module weighs 12 tons on the surface of Earth. How much work is done in propelling the module from the surface of the moon to a height of 50 miles? Consider the radius of the moon to be 1,100 miles and its force of gravity to be 1/6 that of Earth. Okay, so I'm going to say for this problem, we're going to round our answer to 2 decimal places. Just make sure you are paying attention to what the instructions say before you go enter your answers. Okay, so just from a practical standpoint, we've got the moon, and keep in mind this is not drawn to scale. The radius of the moon is 11,000 miles, and we want to propel this thing to a height of 50 miles. So really, we're only going from 11,000 to 11,000. I'm sorry, 1,100 to 1,150. It's not very far, so I put an extra 0 here. Be careful about that. 1,100 to 1,150. So another piece of information that's useful, it says the force of gravity is 1/6 that of Earth. So we know that if something weighs 12 tons on Earth, then it's going to weigh 1/6 times 12 tons, or 2 tons, on the moon. That's an important conversion that we need to make. So we're using the idea that f of x equals c over x squared, because this is a propulsion problem. So I know that when we are on the surface of the moon, when x equals 1,100 miles, or 1,100 miles, then f is going to be equal to 2. So 2 is going to be c divided by 1,100 squared. And that tells me that c is 2 times 1,100 squared, if I get c by itself. So f of x is 2 times 1,100 squared divided by x squared. So my work done here is going to be the integral from 1,100 to 1,150. Remember, we're traveling from the surface to 50 miles above the surface, of the function 2 times 1,100 squared divided by x squared dx. And I can bring those constants out. And I'm integrating x to the -2 dx. This integral is exactly the same one that we did last time. It's just got different units and different constants. So we know that's going to be times -1 over x, from 1,100 to 1,150. So I get 1 over 1,150, or -1 over 1,150, minus -1 over 1,100. So I'll change that negative to a positive. Finding the common denominator here, I get 50, let's see, -1 over 1,150 plus 1 over 1,100. I get 50 over 1,265,000. That's a big fraction, okay? And then when I multiply that times 2 times 1,100 squared, rounding to 2 decimal places, we get about 95.65, and this unit is mile tons. So it would take that amount of work to propel this object.